Welcome to another MEC 1000 video. We're looking at Unit 13 in the Blueprint Reading textbook today at Geometric Tolerancing. So we've spent quite a bit of time this semester talking about dimensional tolerancing, about how even though something might be designed to be a certain length or a certain diameter due to the inherent nature of machining, there are variations in size. So geometric tolerancing is another way to ensure that the parts that are being manufactured meet the requirements of the design, not only in size, but in shape. So this is achieved through a variety of different symbols that are used to describe three-dimensional characteristics of a part, and we can then apply to those parts or features a numerical range in which it can be accepted. So these symbols include a straight line for straightness, a parallelogram for flatness, a circle for circularity or roundness, a circle with two diagonal parallel tangent lines indicating cylindricity, an arc to show the profile of a line, an arc with a straight line across its bottom for the profile of a surface, two lines meeting at an angle for angularity, two lines meeting at a right angle like an inverted T for perpendicularity, two parallel diagonal lines for parallelism, this symbol that looks a bit like a target for position, two concentric circles for concentricity, these three lines, parallel lines for symmetry, and then we have these arrow symbols for circular runout and total runout. So on a drawing, you may see a box like this, which includes a symbol, one of the symbols mentioned on the previous slide, indicating what geometric characteristic is being controlled, and then a numerical value following it, indicating the tolerance, the perhaps plus or minus amount, or just a range of variation that can be accepted. And you may also see a symbol like this indicating that the condition is only applied at this particular symbol means maximum material condition. In addition to the symbol, the numerical value, a symbol like this indicating the material condition, you may also see a letter added onto the end of the box indicating a datum that is being referenced. And I think this will become clearer when we look at some specific examples. In addition to that maximum material condition symbol, we also have least material condition or projected tolerance zone, M, L, and P in circles. That's what those three things stand for. So the datum that is referenced in a geometric tolerance has to be identified somewhere on the drawing, and this is the way it's done. There will typically be a box connected by a line and perhaps like an inverted arrow symbol that can be filled in or not, indicating that that line, that horizontal line, is in fact datum A. You may see a symbol like this that combines the box indicating the feature being controlled and simultaneously identifies the feature as a datum, in this case datum C. This symbol, which we'll see in the next chapter when we talk about weld symbols, indicates all around. This is used often for cylindrical type shapes like a pipe to indicate that the feature goes all the way around the outside diameter of that pipe or cylinder. So the first group of tolerances we're going to look at are called form tolerances. These tolerances include straightness, flatness, circularity, and cylindricity. So straightness indicates that a particular surface or axis has to be straight. And so there is a zone specified, and the size of that zone is indicated by the number in the geometric tolerance symbol. So the element being indicated has to lie within that zone. If it goes outside the zone, it's rejected. But as long as it remains within that tolerance zone, it is an accepted part. So let's take a look at an example here. Here we have a cylinder, and we have this geometric tolerance symbol on it, indicating that it needs to be straight within 0.02 inches. So we might think, well, of course a cylinder is straight. But think of all the ways that it could be not straight. It could bend, it could have a little bit of a bow to it. And so in that case, if we were to measure from, for instance, this lowest point right here at the corner to the highest point in the middle of this arc, and we measured this vertical distance, how far out of straightness it is, that would need to stay within a 0.02 tolerance zone. So as long as that dimension, whatever that is less than 0.02, it's acceptable. But as soon as it's bent to such a degree that that dimension exceeds 0.02, then it would be rejected. Also, we have just a regular old diameter tolerance here, given in the form of limits, a maximum and minimum dimension for the diameter here. So the maximum size this can be a 16, which means from the highest point right here at the peak of that curve to the lowest point at this corner, or this one, that still has to be held within that 16 measurement. I don't know if this is 16, probably 16 inches or 16 millimeters, whatever the units are. It has to be within that 16 to be considered acceptable. In addition to curving, how else could this cylinder be, how could its surfaces be not straight? Well, it could bow inwards in both directions. Okay, so again, this change in dimension from the lowest point to the highest point of that curved surface, according to our geometric tolerance, that cannot exceed 0.02. And the maximum diameter, based on the dimensional tolerance, can still not exceed 16. The third example of how a cylinder could be something other than straight would be if it were to bulge out in its center. Again, what we're saying with our geometric tolerance is that dimension right there from an imaginary straight line connecting the two corners here to the highest point of that bulge, that cannot exceed 0.02. As long as it does not do that, as long as it stays within 0.02, it's acceptable. If it exceeds 0.02, this part would be rejected based on the geometric tolerance. We also need to make sure that our diameter dimensional tolerance is still acceptable as well. So at the widest point of this cylinder, it cannot exceed a diameter of 16. So that's straightness. The next is flatness. This part has this parallelogram symbol indicating flatness, and the tolerance zone is 0.25. So flatness doesn't necessarily mean that it is horizontal. It just means that if we measure from the highest point on that surface to the lowest point, that the difference between those 2 points cannot be more than 0.25. If that difference is greater than 0.25, then it fails its geometric tolerance. Okay, and this can be in either direction and over a two-dimensional surface, picking the highest point and the lowest point. Those differences in elevation can't be more than 0.25. It doesn't necessarily mean, as I said, in this example, this top surface is sloping down. That looks like it's not the intention of the design, but that is not what's being controlled by this geometric tolerance. It doesn't matter that it's sloping down. What matters is the difference between the high and low points. Circularity basically just means that if something is supposed to be a circle, it needs to be a circle. It can't be egg-shaped or pear-shaped or have a flat spot. It needs to be round. So here we have a cylinder. In its cross-section view, we see a geometric tolerance here, circularity, 0.25. And so that means that there is a 0.25 tolerance zone, kind of almost like a donut or life preserver shape going around this circle, both slightly to the outside and inside. And so long as the shape of that circle stays within that tolerance zone, that 0.25 tolerance zone, then it is acceptable. If any part of it goes outside or inside that donut-shaped tolerance zone, then it would be rejected. The last of our form tolerances is cylindricity, and this is very similar to circularity, but we're taking this idea of circularity, of this donut shape, and we're extruding it along an axis. So our tolerance zone is actually kind of shaped like a tube. It has an outer diameter, an inner diameter, and a length. So all along the length of that cylinder, at no point can the edges of that cylinder go outside the tolerance zone. As long as it stays inside the outside diameter and outside the inside diameter, in this case, the geometric tolerance over here indicates the requirement of a cylindrical geometric tolerance with a tolerance zone of 0.25. As long as it stays within that zone along its entire length, then it is passing its tolerance. Its tolerance requirement, I should say. All right, let's look at an example here before we wrap up this first video. So in this example, the first question is, how many geometric tolerances are specified? So I see 1, 2, 3, 4, 5, 6. There are 6 geometric tolerances specified in this drawing. Interpret the geometric characteristic symbol appearing on the front view. So this is the front view. The geometric tolerance appearing here is right there. It's a straight line. That indicates straightness. Interpret the geometric characteristic symbol appearing on the top surface of the block. So it doesn't mean the top view, but the top surface. This is the top surface. And so if we extend that line out here, the geometric tolerance symbol appearing on that surface is this parallelogram symbol indicating flatness. How much geometric tolerance is applied to the cylindricity? So here is the cylindricity symbol. So the tolerance on that is 0.1. How much geometric tolerance is applied to flatness? Here we see flatness with 0.15. Here we also see flatness, same tolerance, 0.15. All right, and that should do it for this video. We'll resume this conversation in the next one.